students. I'm being held at an undisclosed location as part of the witness protection program. You can also not see my face. All you'll know is that I am an Alabama fan. Let's get right to it before someone finds me. So what is hybridization? Hybridization is exactly what you see in front of you. It's the idea of combining orbitals, s orbitals, p orbitals, d orbitals. How do you arrange them to reach the minimum energy possible? That's why bonds form, right? To reach areas of lowest energy. So how can we mix the orbitals together? Now, you've heard of hybrids before, maybe in biology class. What's a hybrid? It's a mixture. So you're a mixture. You're a hybrid of your two parents. So bonds can hybridize as well. So let's see what that looks like. The first one you see right there, that's an s orbital. S orbitals are round. The p orbitals, if you remember, the p orbitals, there are 3 of them, and there's one in each axis, and they have a weird shape. They're not round, they're kind of oblong. The distance from the nucleus is going to be different in the s and the p. So if you look to make a bond, like let's say you want to make 4 bonds, well, you're going to have to tie the electrons in the s orbital, the electrons in the p orbital together with another atom. But they're not all the same distance because the s orbitals are going to be a different distance than the p orbitals. So you don't want to end up with one bond that's longer than the others, because if you do that, then they're not all equal energy. You want to mix the bonds together. You want to mix s's and p's together or hybridize them to get the bond of minimum energy or lowest energy, because that's what nature strives for. As you can see here, I can mix an S and 3 P's together, and by combining red and blue, you come up with what color? Purple. That's right. So if I mix an S and 3 P's together, instead of having one bond that's an S and then 3 bonds that are with P's, I hybridize them together into what's called an sp3 hybridized orbital. And if you notice the purple ones right here, these are the hybridized orbital. Notice they're all the same shape. They don't all stick in the same orientation, but they all 3 are the same shape. They're all the same size. Each one of those will be used to form a single bond. So for something like CH4, that's methane to you and me, we would use one of these, this one right here. How about this one? To stick together the carbon with one of the hydrogens. And then this one over here, we'll stick another hydrogen on, and then maybe this one, and then maybe the last one. And what this gives you is one off the top, and then a tripod coming out of the bottom, and that gives you that tetrahedral shape or geometry that we learned about. By mixing these together, you can come up with different shapes of orbitals by hybridizing them. You take the p orbitals, which have a certain amount of energy, the s orbital, which has a certain amount of energy, you combine them together, and voila, there you go. You get a hybridized orbital that's somewhere in between, so that they all have the same energy. Now, in this example, I didn't use all the p's, I only used 2 of the p's. So I took one of the s's and 2 of the p's and hybridized to give an sp2 hybrid orbital. There's still a 2p sitting out there, right? Because we didn't use that one. And we'll see what that's used for in a minute. So here's a molecule called ethylene. This is ethylene. Ethylene is nothing more than a monomer that you combine together to make a polyethylene molecule. And that just makes sense. That's what you see in like water bottles or in plastic wrap. That's what polyethylene is. Now notice down here, I have a single bond holding the carbons together. And I have single bonds holding the hydrogens to the carbon. But in the molecule I just drew for you, there's a double bond. So what's going on there? When you're forming bonds and hybridizing orbitals, I needed 3 bonds for one of the carbons. I needed one of the carbons to bind to 2 hydrogens. There's 2 bonds. And I also need that carbon to stick to another carbon. Those are the single bonds. So I hybridized an S, you always use the S, and 2 of the P's. And by hybridizing an S and 2 of the P's, that gives you 3 hybrid orbitals. Now I have a P left over. The carbon on the left, it has a P left over because there's 3 P's. I only use 2 of them. The carbon on the right, it also has a P left over. And notice that the sp2 orbitals, see how they're all the same size and all the same shape, same distance from the nucleus? And where they overlap, that's where the bond forms. Well, I still have a P left over, so let's see if we can use that P to make a double bond. And there it is. That double bond exists in the p orbital. That's what's represented here in blue. The p orbital is, I didn't use it, I didn't hybridize it, it's just left over. I can use that p orbital to set up another bond. Now realize that bond exists in the lined areas, in the dotted areas. So that it's not like one bond on top, one bond on the bottom. Those dotted lines represent one bond, an area where you will see electrons being shared. The single bond exists in the green part, the double bond exists in the blue part, and that's how you hybridize orbitals to set up a bond. What about a molecule like carbon dioxide? Carbon dioxide is sp hybridized because if you look at carbon dioxide, we can draw that one for you too. We did this one in class, so this should be no great surprise. And if you remember, we had some lone pairs laying around. So if we look at that molecule, how many things does carbon need to stick to? Well, carbon needs to stick to 2 things. You're going to mix together an S and a P. When you mix together an S and a P, you'll produce an sp hybridized orbital. We use one of those sp hybrids over on the right and one over on the left. That's what the yellow stuff is. But realize carbon has 3 p orbitals, correct? Well, we only use one of them. How many are left? No, not 3. 2. Yeah, that's right. We have 2 left over. So keep that in mind. That carbon is 2 left over. That oxygen has 3 places where it needs to put electrons. One place it needs electrons is in the bond to carbon. That's true. And the other place it needs electrons are for those lone pairs. So you're going to make those hybrid orbitals as a place to put electrons. You want all of those orbitals to be the same shape and distance, to be a mixing of energy levels so they're all the same. So for one of those lone pairs, we need a hybridized orbitals. For the other one of the lone pairs, we need another hybridized orbital. And for the bond with the carbon, we need a hybridized orbitals. So that's 3 places where we need electrons. So we're going to use an S and then 2 of the P's. And so there we have sp2 hybridized, and that gives us all those single bonds. Notice, the same thing is true of the oxygen over on the right-hand side. It did the same thing, right? So right now, all we have is single bonds. So where does a double bond come in? The double bond comes in right here. You'll notice that the oxygen was sp2 hybridized, and so it had a P left over. So that's why the oxygen has the blue P. And remember, carbon had 2 P's left over. And so the carbon uses 1 P orbital to bond to the oxygen's P orbital. That's the double bond there. And then carbon uses its other P orbital to bond to the oxygen on the right with its P orbital. We hybridized for the first bond. That first bond is always going to be called a sigma bond. The first bond that forms is always called a sigma bond. The second bond that forms is going to be called a pi bond. So, for example, in carbon dioxide, how many sigma bonds do you see? 2. 1 here and 1 there. And how many pi bonds do you see? 2 as well. 1 here and 1 there. And that's pretty easy. So, how do I figure out what kind of hybridization do I do? Well, for carbon dioxide, carbon, what kind of hybridization is it going to show? How many things does it need to stick to? 2. I'm going to use an S and then 1 of the P's. And what about oxygen? How do we figure out what hybridization oxygen uses? Well, it needs 3 places to put electrons. 1 to stick to the carbon, and 2 for its lone pairs. So that's going to be S, always use the S first, and then 2 of the P's. And that's a total of 3. And I'll show you how to use your fingers in class to do this, but hybridization is actually pretty simple. So just to reiterate, a sigma bond is always the one on the internuclear axis. So between the 2 nuclei, that first straight one that came in, where we hooked them together, that's called a sigma bond. A pi bond always occurs second. So a double bond is a sigma and a pi. And a triple bond is a sigma and 2 pi's. It's just that easy. So the first one that forms is always a sigma. The second one that forms is always a pi. The third one that would form is also a pi. Now that I've been saying pi so much, I'm hungry. All right, to close our time here, all I want you to do is look at this molecule. Realize that here on the end, this carbon is single bonded to the 2 hydrogens. So every time you see like a CH2 or a CH, that means there's a single bond between that carbon and that hydrogen. So what I want you to do is take this molecule, kind of draw it out, and I want you to do 2 things for me. I want you to figure out what the hybridization of each carbon and oxygen and nitrogen are. Hydrogen never hybridizes. Figure out what the hybridization of each carbon, oxygen, and nitrogen are. And then also add up the number of sigma bonds and then figure out how many pi bonds there are. All right, that's it. I'll leave you with an image of some pie. Go have some pie. That sounds delicious.